Okay, let's make a start. First off, welcome. Thank you all very much for coming. I'm Rob Julian. I'm a medical physicist with OSL. I'm just going to mention a couple of practicalities, and then I will hand the floor quickly over to my colleagues at RTsafe, who will be leading the presentation. So in terms of practicalities, we have two presenters today, each of whom will give about 10 minutes, and there should be a little bit of time at the end for questions. Regarding questions, if you could type them into the meeting chat, and we will address them all, or as many as we can at the end of the session. If anything doesn't get addressed during the session, do feel free to reach out afterwards, and we will do the same if we spot that your question hasn't been answered. The webinar is being recorded. If you would like a copy, if you're in the UK and Ireland, please reach out to me or one of my colleagues at OSL, or overseas if you reach out directly to RTsafe. And with that, all that remains for me to say is to welcome and to hand over to our first presenter, Aliki.
Thank you, Rob. Good afternoon to you all. I would like to thank you for attending this webinar. So SRS and SBRT present the most demanding clinical applications in modern radiotherapy. And in this presentation, we will focus on the importance of dosimetric accuracy, the challenges introduced, and how end-to-end verification using our solutions enables objective and independent assessment of clinical performance. So, why accuracy matters? SRS and SBRT are multi-stage, highly complex processes that require sub-millimeter geometric accuracy and high dosimetric precision across the entire treatment chain. So, traditional QA is no longer sufficient. Accuracy matters because potential errors can occur at every stage of the treatment chain. This includes CT or MR imaging, treatment planning, dose calculation, patient positioning, image guidance, and as well as dose delivery. So minimizing uncertainties leads to safer and more effective stereotactic treatments. SRS and SBRT are characterized by very high doses per fraction, small radiation fields, and extremely steep dose gradients requiring the highest levels of accuracy and precision. End-to-end testing is essential to ensure patient safety and to build clinical confidence in delivering precise, high-quality stereotactic treatments. And here are our solutions. RTsafe offers integrated end-to-end solutions for stereotactic radiotherapy. The PRIME and SBRT anthropomorphic phantoms provide realistic patient-like scenarios for throughout testing of the entire radiotherapy system. These are supported by advanced dosimetry and independent audit services, enabling quality improvement, promoting best practice, and assuring accurate and compliant SRS and SBRT treatments. So we can start with our phantoms. We have the PRIME phantom, that is a 3D printed head phantom, which incorporates bone and soft tissue equivalent materials. It provides realistic contrast in CT and MR imaging, is compatible with MR, CT, CBCT, and MV imaging, and we can treat it exactly like a real patient. This makes PRIME phantom ideal for true end-to-end SRS verification. So this phantom, prime phantom, as well as SBRT phantom, as we can see in the next slide, are accompanied by inserts suitable for OSL dosimeters. We have one from RadPro, radiochromic films from Asland, and polymer gel dosimeters, allowing in this way point 2D and 3D dosimetry. In addition, we have MR-related geometric disruption evaluation that can be performed with the insert we have for MR. The second basic phantom we have is the SBRT phantom that likewise prime phantom stimulates this phantom simulates abdominal anatomy, including lung and liver structures using tissue equivalent materials as prime. This is compatible with for online adaptation and of advanced SBRT techniques. So also SBRT phantom is equipped with dedicated inserts for OSL films and polymer gel dosimetry. Beyond the previous two standard phantoms, RTsafe also offers a fully customized phantom service. So the end users, clinics, becomes a part of the design process, and they can participate in defining geometry, materials, the dosimetric needs, resulting in phantoms tailor-made to specific clinical and research questions. Later on, Vasiliki will talk about that in some cases. The third solution we have, it's our audit service that we provide an independent SRS and SBRT audits using the prime and SBRT phantom combined with OSL film and polymer gel dosimetry. As we can see, we have 17 calibrated OCLDs. For 2D dosimetry, we have a pair of EBT4 film, and for 3D gel dosimetry, we have a gel-filled cylinder. This is for evaluating the entire treatment chain with ready-to-use dosimeters, fully traceable to the secondary standard dosimetry laboratory, while requiring minimal effort from the clinic. That's pretty much a plus for the clinics. Okay. After the audit, we give the clinic a comprehensive audit report, which includes 1D dose profiles and gamma analysis. We have 2D isodose distributions and gamma maps, and lastly, 3D gamma passing rates. So geometric offsets between planned and delivered dose distributions, they can quantify. Overall performance is assessed using tolerance limits proposed by the WPM physics guidelines for SRS and SBRT treatments. Here we can see our audit workflow. We can see each step for our process, which pretty much begins with downloading the reference dataset we give to the clinic. followed by the receipt of the prime or SBRT fundum with the pre-cutted, pre-calibrated, traceable dosimeters, as I said before. Then the clinic has to treat the fundum as a real patient. The fundum undergoes the complete clinical SRS or SBRT workflow, including everything I said: imaging, treatment planning, positioning, image guidance, dose delivery, of course, according to the clinic's local protocols. After treatment, the data are uploaded from the clinic. The fundum with the irradiated dosimeters is returned to RTsafe for measurement and analysis. And as we can see, the workflow concludes with the delivery of a comprehensive dosimetry audit report we give to the clinic, providing an objective evaluation of dosimetric and geometric accuracy. So this slide summarizes RTsafe's experience in dosimetry audits. As shown here, we have performed a large number of SRS and SBRT audits. We can see we have performed more than 120 audits all over the world, involving over 30 radiotherapy departments and 6 different radiotherapy systems. So we can say we have the experience, and I can say that we can build clinical confidence, we can support and identify and correct of any uncertainties one clinic could have, and help the departments achieve more efficient stereotactic treatments. So now I will hand over the presentation to my colleague Vasiliki.
Thank you very much.
Thank you all.
Thank you very much, Aliki. Good afternoon. Except for the end-to-end QA procedures and audit tests, our products and services can be used for commissioning and benchmarking of radiotherapy treatment modality, such as Linux, Gamma 9, Cyber 9, as well as MR Linux system, for supporting the SRS program modalities, for clinical or academic research, or educational and confidence building purposes. Regarding the clinical and academic research, a recent study used our prime phantom in order to perform dosimetric and positional validation of the plan adaptation and high definition motion management system of a Gamma 9 system for various clinical scenarios. As I said, the prime phantom with a film dosimetry insert was used throughout the study. Clinical treatment plans were generated using the Lexel Gamma Plan software. Regarding the plan generation, here in this image, you can see the corner view of the location of the 5 shots, as well as the sagittal view of the marker noise marker, the rotation axis, and the film insert. A total of 13 distinct motion and setup scenarios were tested, including motion near high-definition motion management threshold, coughing, and other setup errors. One of the dosimetric deviation that was studied was for the chin up and chin down displacements near SGMM alarm threshold. According to the results, a significant dose reduction up to 7% and 13% was noted in sink down position and for the 2 millimeters and 3 millimeters ACMM alarm threshold, respectively. Furthermore, the deviations for multiple interruptions during treatment that required plan adaptation, as you can see in this figure, were minimal. Also, the dosimetric deviation for patient coughing at the 1.5 millimeters ACMM alarm threshold were below 2%. Regarding any displacement of pitch angle up to 20 degrees during initial setup, the dosimetric deviation were measured to be 3.5%. In general, this study shows that the gamma knife system has a reliable dosimetry accuracy even under challenging motion. Apart from this, with increasing number of brain metastases, single target SRS becomes less efficient and feasible. This led to the development of single isocertain multi-target SRS, which is a more challenging technique. In order to evaluate variation in protocols, infrastructure planning, and QA for this technique, a multi-center study was performed. This survey was performed across 23 radiotherapy centers in Germany, Austria, and Switzerland. A reference case was defined based on our prime phantom. The prime phantom was used accompanied by ion chamber detector and polymer gel dosimeters. For the purpose of this study, 5 spherical target volumes were included in the reference structure set. Through this irradiation, a large interest in tissue variability was noted in planning, delivery, and quality assurance procedures. There was some consensus on some key techniques such as high-resolution imaging, 6 degrees of freedom setup, and non-compliant delivery. The major differences were observed in interfraction motion control, the target site limits, QA methods, platforms, as well as planning parameters. In addition, the more experienced centers tended to apply stricter planning criteria and advanced imaging verification. Overall, the findings of the study highlight the need for more harmonized guidelines in order to improve standardization, safety, and reproducibility of single isocenter multi-target SRS practices. Last but not least, as I mentioned before, our prime phantom can be used in MR-Linux system. A recent study used prime phantom in order to access a 3D geometrical accuracy and reproducibility of an online adaptive radiotherapy workflow in an MR-Linux system. The prime phantom with a gel-filled cylinder and a film dosimeter insert was used. All measurements were performed in a clinical Unity MR-Linux. The gel dosimeter was used mainly to determine any 3D geometric offset, while film dosimetry was performed for comparison against the gel-based measurements. So, based on the measured displacement results, both the geometric accuracy and reproducibility in a Unity and Marina system were evaluated. Based on the measurements, the TPS and JL measurement show a good agreement. And a mean gamma passing rate was 98.2% for a global 3% 3 millimeter gamma criterion. Regarding the geometric shift, in the upper figure, you can see the geometric displacement in each axis respectively, separately. And on the second figure, the 2D displacement for in coronal and sagittal plane, as well as the 3D displacement for the gel measurement are presented. The results show 0.3 millimeter geometry offset for 3D gel measurement and 0.6 millimeter for in-plane film reference measurement. Based on the study, these findings can support 3D gel dosimetry as a useful and accurate tool in order to evaluate the accuracy of the MR Linux system, while the 3D gel dosimetry show good agreement with film dosimetry. Thank you for your attention.